welcome to the class today. My name is Negedu Godwin and I'm your regular anchor. So today we're going to be looking at digital ultrasound devices. I want to express my sincere appreciation to these wonderful people who have contributed greatly to my knowledge. So digital devices, let's get into it. But before then, I'll be right back. Eyes Global Health Services wants you to join the movement. Help us reach a wider audience with a simple click. Like, share, and subscribe to our YouTube channel at youtube.com/@negeduscopy. Turn on notification and get our free lectures as soon as they drop. For more information about our paid classes, contact us on sonoeyesdiagnostics@gmail.com or send a message on WhatsApp to +234 9019 144 175. Visit our website at sonoeyes.business.site for best diagnostic capacity building courses. Don't forget to attempt all the quizzes in our video description and leave us a comment. Sono Eyes Global Health Services, building diagnostic capacity in Africa. You're welcome back. Digital devices is the topic, and we'll do a good job on explaining how we got here in ultrasound diagnosis. An analog signal is a signal that has a continuous spectrum of values. The echo from the tissue interface are analog signals also. So the radio frequency RF signal that is produced in the transducer that correspond to those echoes from the tissue interface are also analog electrical voltage signals. So presently, we live in a digital world. Digital systems represent signals in binary numbers. Advantages of converting an analog signal into digital signal are numerous. These include vastly increased consistency, reproducibility, pre-processing and post-processing data transfer and storage. All modern ultrasound systems are digital systems. So in these systems, the analog RF signal from the transducer is converted into a digital signal so that the advantage of digital processing can be applied to the signal. The process that converts analog signal into digital signal is called analog to digital conversion, or ADC. ADC circuit looks at each echo RF signal from the transducer and assigns it a digital value, a binary number that is proportional to the signal's amplitude. Weak signals will receive small digital values. Strong signals receive a larger digital value. The range of digital values available will depend on the bit capacity of the digital system. That is the size of the microprocessor in the system. After the storage in the memory, each digital value will represent a different shade of gray in the display image. The digital image that may need to be converted back into analog form will depend on the display and the storage device that is being used. All the older video monitors, cameras, VCRs are analog devices. The process that converts digital into digital image data back into analog form is called digital to analog conversion, as DAC. Most modern systems are using digital display and recording devices such as LCD display, picture archiving, and communication system packs, or other digital storage like You have magneto-optic disc like CD-ROM, DVD, Blu-ray, pen drive, and so on. In these systems, the DAC is not required because they are already digital. So digital storage maintains the advantage of a digital system and allows most processing, measurement, and all other functions to be applied to the stored image in system memory. To understand digital system and how the storages are done, we'll look at binary system. And the word binary means two. The binary system is a number system that is used by any digital system because it consists of only two digits, the 0 and 1. The abbreviation for a binary digit is the word bit. That's to say 0 and 1 are bits. A combination of these two bits can be used to represent any value. The binary system is a practical numbering system for digital systems because the electrical components are designed and able to work in the environment reliably, quickly, and efficiently. The numbering system that we are using in our everyday life is called the decimal system. We like it, of course, because we're already habitual with it and we can handle it easily. But the decimal system is too complex for the machine because it contains 10 digits, that is 0 to 9. In decimal system, it is written in base 10, whereas in binary system, it is written in base 2. And just to mention, there are various systems of numbering, but the one we are popular with is the decimal system, and in digital world is the binary system. So the binary system is written only in two digits, 0 and 1. In a decimal system, any value can be represented using a combination of the 10 digits 0 to 9. For example, the combination of 356 represents the value 356. Here, each column of digits holds the value which are 10 times greater than the values held in the column to its immediate right? That's to say 356 represents 3 times 100, 5 times 10, 6 times 1, which can also be written as 3 times 10 to the power of 2 plus 5 times 10 to the power of 1 plus 6 times 10 raised to the power of 0. We are so familiar with the decimal system that we can look at 356 immediately and know that it represents 356. But in the binary system, any value can be represented using a combination of these two binary digits we talked about, just like the decimal system can represent any value. But rather than each column holding values which are 10 times greater than its neighbors, the column in the binary system are double. They are usually double the value of their neighbor. And this table below is an example of an 11 columns from the binary system. In the decimal system, a combination of 3 digits are needed to represent 356. But that in the binary system, a combination of 9 digits, that is 9 bits, are needed to represent the same value. So the larger the value, the more the bits are required to represent it. So this table shows the calculation of for decimal system and for binary system. To calculate the number of different values that can be represented by a certain bit size, we can use the following formula. The number of values is equal to 2 raised to the power of n, and where n is equal to bit size. That's to say, the value 356 can be represented by the binary number 10110010 100, and this is the calculation below to help you understand that and the application of the formula for bit size. The binary system's advantage over the decimal system is that the binary system only uses two symbols or states. That is the 0, which will mean off, and 1, which will mean on. Computers function much better when their environment is composed of only two states, the off and on state. By combining multiple circuits, each of which is either on or off, the computer can use the binary system to represent any value. And since the computer can also process the circuits at an incredible speed, the enormous number of circuits that must be used does not present any problem. Now, let's go into the system and see how these things work. And all this plays out in the digital scan converter, the memory. Now, the digital scan converter, which is the component of the ultrasound system in which the image is constructed, forms the system's memory. Digital memory device has the following advantage over the older analog scan converter. The data is stable. Once the echo amplitude is converted into a number, it drifts or changes. The data can be processed easily simply by manipulating numerical value of data in the memory. That is the second advantage. And the third advantage is mass production of RAM chip in recent years has dramatically increased the capacity of digital memories. This permits the modern digital scan converter to store multiple frames of data in memory that can be instantly recalled by the sonologist at the touch of a button. Now remember, in the other lecture, we talked about the metrics in the scan converter, the memory. So physically, the digital scan converter is a computer memory chip that consists of metrics of squares, like you have in the chessboard. Each square in that matrix is called a pixel or an address location. Now, each pixel or address location is used to store the echo data from the tissue interface occurring at that location. A common digital image matrix has a dimension of 512 by 512 pixels. So the total number of storage location is actually the product of the rows and columns of the pixel. For the 512 by 512 matrix, this represents a 262,144 pixels. That would be roughly 1/4 of a million address location. That's a lot of pixels. However, if we think of the advances in modern digital cameras, we can see that 1/4 of a million is likely the barest minimum that is needed for a good quality image. For example, the standards in present-day digital cameras are 5 million pixels. You begin to understand. So the total number of pixels in the memory determines the memory spatial resolution. The more the pixels they are, the better the spatial resolution of the image. Now let's look at bit capacity or bit depth. The number of different shades of gray, the grayscale that can be used in an image will depend on the bit capacity of the digital scan converter. For example, a 1-bit system having only one layer can only store one of the two different values at each pixel or address location. But a 5-bit system having 5 layers could store any can store more than, because you have 2 to the power of 5, that is 32 values at each pixel. So modern digital memories are typically having like 7 or 8 bits deep at each address location. But look at 7 bits deep memory could store about 2 to the power of 7, that is 128 values, and that's becoming larger. The greater the bit capacity, the greater the number of values that can be used to store in the echo amplitude. Bit depth determines the grayscale, because the greater the range of the digital value that can be stored at each location, the more shades of gray that can be used in display, and the better the gray scale or the contrast resolution of the image. That's to say, the grayscale is proportional to the bit depth of the system. The number of available grayscale shades can be determined from the following equation, which we've talked about before. Number of grayscale shades is equal to 2 to the power of n, and where n represents the bit capacity of the scan converter. So the base 2 is used here because the digital memory uses binary numbers rather than the decimal number system, which is base 10. Modern scanners usually have a bit capacity of at least 7 bits, with some of them being 8 bits system. Now this provides about 128 to 256 shades of gray in modern imaging. So this table gives us the digital storage units and what they occupy. So you have a kilobyte, and a single unit of digital data will be 1024 bytes in a kilobyte. Megabytes, you have 1024 kilobytes in a megabyte. Gigabyte will be 1024 megabytes in a gigabyte. And a terabyte, we have 1024 gigabytes in a terabyte. Remember, contrast resolution is a contributing factor to the overall image quality. Contrast resolution is the ability of an ultrasound system to separate echoes by displaying them with different shades of gray in the grayscale. It is also called grayscale resolution. A system that has good contrast resolution is able to separate the returning echo into wide grayscale range. A system that has poor contrast resolution assigns all the returning echoes a limited range of grayscale. Now this will result in a more contrasty black and white image. Typically, abdominal scan uses a wider grayscale. A subtle change in the grayscale may be the only indication in liver scan of underlying pathology. But in echocardiography and in vascular scanning, a slightly more contrasting image helps define the cardiac chamber and the vessel lumen. So contrast resolution can be described in terms of dynamic range of echoes that can be assigned a gray shade of gray. For example, if the dynamic range of echo intensity returning from the transducer from a 1 milliwatt per centimeter square to 1 million milliwatt per centimeter square, this can be expressed as a dynamic range of 1 million ratio 1, or 60 decibels. This calculation is done in our last lecture. I want you to take a look at it and understand how we arrive at 60 decibels. Using a system that can only assign 2 different shades of gray, the contrast resolution could be calculated by dividing the dynamic range of 60 decibels by the two available gray shades. And when you divide that by 2, that will be 30 decibels per shades. This would produce a black and white display with very poor contrast resolution. With this system, two adjacent echoes could only be differentiated from each other if they were at least 30 decibels different in intensity. In other words, one echo would need to be 1,000 times more intense, that is 30 decibels, than the other for it to be assigned the other shade of gray. But if it's not so, it will be lumped up as one echo, and that becomes poor image quality. On the other hand, if the same dynamic range was assigned like 20 shades of gray, the contrast resolution would be 60 decibels per 20 shades. That would be, when you do the maths, that would be 3 decibels per shade, vastly improving the contrast resolution and making the display much more contrasting. Now, with this system, an echo needs only 3 decibels difference in intensity. That is a factor of 2 to be assigned a different shade of gray. It will be typically the dynamic range of the signals coming into the scan converter is 40 decibels. Since modern ultrasound system can display 256 shades of gray, we can see that modern ultrasound system have an excellent contrast resolution, which is 0.16 decibels per shades, and that is a good resolution. So how can contrast resolution be improved? How do we improve it? Contrast resolution improves as the numerical value for the resolution decreases, as with other types of resolution. You have the axial, lateral, and so on. Since the contrast resolution is expressed in terms of decibels per shades, the resolution will improve if either number of the shade of gray increases or if the dynamic range of the echo signal decreases. Now, since the dynamic range of the echo signal is fairly constant at about 40 decibels, the recent improvements in contrast resolution have occurred due to increase in the number of shades of gray that the system are capable of displaying. Now, this is a function of increase in bit depth of the microprocessor in our modern day computer memories. The digital converter or the memory is divided into metrics of thousands of pixels. The anatomic area stored at each pixel depend on image size or the field of view. For example, consider an image that is stored in a 512 by 512 memory in which the field of view is 20 centimeter. The depth of the tissue can be stored in each pixel in vertical axis of the scan converter can be determined using this calculation. Now 20 centimeter is divided by 512 pixels, which is 200 mm divided by 512 when you convert centimeter into mm. Yeah, so the answer will be 0.4 mm per pixel. So in this case, each pixel represents a linear distance of 0.4 mm. If the memory's spatial resolution capacity or capability is less than the axial resolution of the transducer, this echo will not be displayed as a separate echo in the image. In this case, the memory has a spatial resolution of 0.4. Let's compare this resolution to the axial resolution of 3.5 megahertz 4-cycle pulse in a soft tissue. Such a pulse will have an axial resolution which is equals to SPL, that's spatial pulse resolution, divided by 2, which is 0.9 mm. You can see that in the above case, the digital scan converter has a better resolution than the beam or the transducer axial resolution, which is 0.4. It's less than 0.9 mm and will not be a limiting factor in the system overall spatial resolution. But again, let's compare the same digital scan converter resolution to axial resolution of a 10 MHz high frequency transducer with 4 cycles pulse. In this case, the transducer axial resolution normal formula SPL divided by 2 is equals to 0.3. In this case, the axial resolution of the transducer is better than the memory spatial resolution for the field of view. Memory spatial resolution of field of view is 0.4, which is greater than 0.3 mm. So two reflectors that are separated 0.3 mm could be resolved by the axial resolution of the beam, but could not be separated in the memory. In other words, they become lumped up as one image instead of separation because of that difference. So in this case, the memory resolution of the scan converter will be a limiting factor to the system overall spatial resolution. So how can we improve the memory resolution? There are several factors which can help provide better spatial resolution. The first will be the use of a large digital scan converter memory matrix. That is 1024 by 1024 pixel memory matrix will essentially double the spatial resolution. So in this case, each pixel could represent a distance equal to half of that in our previous example, which is 0.2 mm. Even in the 10 MHz transducer with an excellent axial resolution tree of 0.3 mm, the scan converter spatial resolution will be superior to the beam resolution and will permit all the reflectors to be resolved by the transducer. The second way is use a shorter depth of field, which is another simpler method of improving image spatial resolution. You use a shorter FOV. Let's consider our first example again. If the depth of field is 15 centimeter instead of 20 centimeter, the pixel dimension becomes 15 centimeter, which is, when you convert it, is 150 mm divided by 512 pixels, which will be 0.3 mm per pixel. So with a depth of field of 15 centimeter, the memory resolution will be adequate for both the 3.5 megahertz, which is 0.9 mm spatial resolution, and 10 megahertz transducer, which is 0.3 mm. That's to say, to ensure adequate image spatial resolution, the sonologist should always select the shallowest depths of field, which will permit better display at the area of interest. As a rule of thumb, for good memory resolution, large digital scan converter memory matrix is the first thing to consider. Then use a shallow depth of field, as FOV. I want to thank you for joining this lecture. Please like, share, subscribe, and put on notification to receive all our free lectures. Sono Eyes Global Health Services wants you to join the movement. Help us reach a wider audience with a simple click. Like, share, and subscribe to our YouTube channel at youtube.com/@negedoscopy. Turn on notification and get our free lectures as soon as they drop. For more information about our paid classes, contact us on sonoeyesdiagnostics@gmail.com or send a message on WhatsApp to +234 9019 144 175. Visit our website at sonoeyes.business.site for best diagnostic capacity building courses. Don't forget to attempt all the quizzes in our video description and leave us a comment. Sono Eyes Global Health Services, building diagnostic capacity in Africa. Until the next time when I come your way again, keep learning ultrasound.